And there we are.
We're live. Look at that.
Hello, David.
Hey, John.
All right. So currently we have
No watching?
39 waiting. I don't know what it's. We are live though. Hooray!
You on Twitter and see who's like.
I did the Twitter thing.
Everyone's okay.
Yep. So it's been a while. I don't even know when the last time you were on was.
Yeah, me neither. I think maybe the first year we were doing the stand-ups or the second year. I can't remember.
Which I think was like 1834 or something.
Yeah.
Wow. All right. Well, people definitely are happy to have you on. We're already up to 60 viewers.
Woo, cool.
So yeah, cool. So one nice thing with this now these days is the chat is actually preserved on these. So it used to be with the chat as soon as the thing ended, it was just the chat was gone.
Yeah.
But now it stays around. So very good. Hello, people on the chat. Cool.
Hey.
Well, so you've got a lot of cool stuff to show off.
Yeah.
Let's get started. First thing, I do not have community links this week. We're just gonna go right to the goodness. So.
All right. So just my content.
Just you.
All right. So I'm gonna show today a thing called Bedrock, which I've been tweeting about for the last couple of months now. I'll show a little bit of new SignalR. We are just finishing the RC milestone. So we are making much more changes. And for RTM, we're in this thing called ask mode. So we have to ask for everyone to be fixed. So we're kind of like having less things going in, less churn, so we can finish off ASP.NET Core 2.1 overall. So let me share my screen. Is it working? Is it good?
It's me.
All good?
Yep. All
right, so let's talk about the history of things. In 1.0 of ASP.NET Core, we made a server called Kestrel, which everyone kind of knows and loves. Kestrel was our web server. It was built on this thing called libuv. libuv is a cross-platform networking library for Node.js. It was made by the Node.js guys so that they could have a cross-platform networking story for Node. We took it because there was no networking story cross-platform in the very beginning of ASP.NET Core days, before .NET Core was cross-platform. So historically, we kind of used it as our cross-platform networking library. In 1.0, and I kind of want to show you this repository because one of our devs always complained that Kestrel got more complicated when we added more stuff to it. So my job is to make things more complicated, I guess, or simpler. If you look at Kestrel 1.0, the source code, you'll see it has two projects, Kestrel and Kestrel HTTPS. So very simple. This is the web server. This is HTTPS support. Contrast that with what we have today in the dev branch. Then we have core, HTTPS, abstractions, libuv, sockets, Kestrel, connection abstractions. And the idea was that we wanted to actually break Kestrel down into more layers so that you can use the layers separately, because most projects need a good networking stack, and we kind of ended up with that in Kestrel. So 1.0 is very simple. There was a type called socket input in Kestrel 1.0, and it was kind of the core library used to do I/O between libuv and the application layer. And I saw it as this and that was actually written by Louis Desjardins, who actually is on the Bing team now. And it looked like a very generic thing that could be used for any networking protocol. So I was like, we should make this a BCL thing. So I made this repository called channels under my private GitHub repository, where I kind of incubated this push-based streams idea for .NET. And I got a couple of guys involved from the community. So you guys know Mark Gravel from Stack Overflow. Let me try to find his commits on here. Started helping out because they make Stack Exchange Redis. Mm-hmm. And Tim Seward, who actually works at a bank, and he was doing some SSL things. And of course, Ben Adams, because Ben is everywhere. At all times. Ever seeing Ben. And we ended up incubating this thing. And it ended up, we ended up using new patterns and new practices and buffer pooling. And the whole idea was that we turn this thing into a general purpose library that can be used for networking. So what ended up happening, we ended up moving this library to CoreFX. And it got renamed to System I/O Pipelines in CoreFX. If you don't know, CoreFX is where we incubate ideas for vNext of .NET. So things kind of start off in CoreFX Lab. So for example, we have this System Azure experimental. We have basic support primitives here. We have buffer readers, buffer writers, multi-value dictionaries, sequences. Basically, it's a kind of a hodgepodge of stuff that we have as ideas. And the goal is that we incubate here, iterate a little bit, push packages, people try them out. This is completely unsupported. And then we eventually migrate from this to CoreFX. So if you look here closely, you'll see there's no more system I/O pipelines in CoreFX Lab because we actually put it into CoreFX proper in 2.1. So if you look at the latest 2.1 CoreFX, you'll see under source, there's a system I/O pipelines. Oh my gosh, there's a lot of stuff here. Not pipes, that's different. Pipelines right here in CoreFX. So now we have an official packaging in 2.1 for pipelines. That's on NuGet. I'll explain what those are as we move forward. In parallel, while I was working on channels, I started to prototype new SignalR, and we had this abstraction layer called ASP.NET Core Sockets, which is an awful name. But the idea was that sockets is this generic networking abstraction where you're hidden away from the actual details of the transport. So you were libuv, or you were sockets, or you were Rio, which is the Windows specific networking APIs, or you were name pipes, or you were unit sockets. You could code against a single abstraction and not have to worry about the underlying transport layer. And that was one of the main things, because previously in SignalR, people would ask if you could host it on, for example, like name pipes to do IPC between processes. So this is the original SignalR repository. It's actually moved now to the official ASP.NET SignalR. If you look in the commit history, you'll see a bunch of things in here, like sockets using SignalR, and we kind of had a bunch of prototypes for doing generic networking things on top of this new sockets layer. So that happened, and then in the end of 2.0, we shipped pipelines as source in Kestrel because we weren't ready to make it public yet. So Kestrel actually has the source of pipelines checked in the 2.0 branch, which could be a nightmare for servicing, but works fine. So after going through a bunch of these various things, I wrote this Uber spec for Bedrock, and I found an issue on Kestrel. I kind of laid out the plans for what I thought we should do going forward in ASP.NET to support our non-HTTP networking stack. So the idea here is there's kind of two parts. And I have some like super ghetto diagrams I made last night. That made no sense, but bear with me. Applications are kind of things that live on top. So ASP.NET Core is an application, for example. SignalR is in the same category of as application. The dispatcher is the thing that gets your configured pipeline and calls it. So think of this as like hosting, for example. The transport is the thing shuffling bytes back and forth. So transport layer, for example, would be sockets or name pipes or whatever else can read and write bytes. So
that's something I would write.
Yeah. I don't think it's for everyone to write. It's for people who understand. So the goal here is that if you write a framework and you need networking, so let's say you wrote a MongoDB driver for a database. You are an application layer. You sit on top of the dispatcher, and you write against some arbitrary connection abstraction. And the transport could be libuv or it could be sockets. But the idea is that the person that wrote the transport layer understands transports, understands how to optimize their capital of them. So the transport layer is super fast. And the application layer just codes against this abstraction. And then you're decoupled from the underlying transport layer completely. So the idea is that we would ship transports like libuv and sockets that are highly optimized for TCP scenarios. And then Ben's going to ship Rio because Ben's going to do Rio because I made him to do that. He signed up for it. And application layers can take advantage of arbitrary transport layers that come off the shelf. So the idea is that you shouldn't have to worry too much about the underlying networking layer, and that you write applications that run anywhere.
So for people that don't know, and we're getting some echo, by the way, I know it's kind of coming in and out. The Rio is the thing where it's directly accessing the network, like the memory, right? It's direct.
Yeah. So Rio stands for registered I/O, and the way it works is you give Rio a bunch of memory that it pins to physical memory to do I/O. And then there's no kernel switches whenever you actually do reads and writes. And you're managing everything yourself, all the buffers. So there's no layer below you. You're basically given control of networking, talking to like physical memory, which is insanely fast, but insanely hard to do sometimes.
Okay.
Yeah. So this issue kind of spells out the layers, and the idea is that we want to have a support for non-HTTP protocols in ASP.NET Core. So ASP.NET Core is basically an umbrella term for like server programming. So don't think of it as like ASP.NET Web Forms or whatever. The name is a brand, and the brand supports multiple like things other than HTTP. It's not tied to HTTP. I know people. Has anyone said WCF yet on the chat? No one said it?
Nope.
Oh, good. Awesome. That always comes up when I show these slides. The goal isn't to be as high level as WCF. It's more like this is the underlying thing that you could build on top of, right? If you were going to build a new WCF, you could use this as the networking stack. If that makes sense. There's a popular protocol called MQTT. I don't know what it stands for. Something, lightweight, something small. It's used in IoT scenarios, and it's I think I don't know if it's as popular as HTTP. It's kind of the next level below HTTP when you're talking about IoT. It comes up in all the things that do IoT. It's a binary protocol over TCP or WebSockets, and it has a spec, and there's a bunch of libraries in .NET for doing this stuff. So you can imagine writing a server app that supports both HTTP and MQTT in the same application with similar patterns. So the goal here is to be able to unify those kinds of things, and not have to worry about varying abstractions that are built on. So I called out the various layers. There's kind of application, middleware, frameworks. They're kind of the same in the same space. So yeah, the application code handles connections and implements the protocol parsing logic. So for example, if you had a socket and you want to implement your own protocol, you would have to read from the socket, parse some data from the stream, and encode it into some message, and then do some other stuff, right? For middleware, there are things that run kind of wrap the stream of data. So for example, TLS, or I guess people know as HTTPS for HTTP. TLS is the encryption and decryption logic around the actual stream. So as an example, whenever you, as the TLS middleware, whenever you read from the stream, it will decrypt from the actual underlying transport and give you unencrypted bytes. And when you write, it would encrypt those bytes and write to the underlying transport. As an example of middleware. And then dispatchers are basically the things that call into the middleware pipeline for connections. The idea was to build parallels to the HTTP layer. So there's a connection context, there's an iConnection builder versus the iApp builder. If you can recall, I can show it just in case everyone's super confused right now.
Yeah, as you're bringing that up, we got a question.
Yeah.
Will UDP be possible with SignalR?
Not really. So the biggest thing about the current Bedrock abstraction is that it requires connection semantics. So UDP is connectionless. You just send and receive from an arbitrary address. There are other things on top that might work that may work better than just raw UDP. Let me just jump forward. So there's this thing called QUIC. This protocol that's coming out called QUIC, and stands for Quick UDP Internet Connections. It's basically, if I were to TLDR, it would be, it's UDP. It is trying to create a connection layer on top of UDP. So it's kind of like TCP on top of UDP, and it merges in TLS into the same protocol. And this is actually used today. If you use YouTube, QUIC is actually being used under the covers. So I think it may not work for raw UDP, but I think if you did UDP with connection semantics, where you had a connection ID as part of your packet, you could make SignalR work that way, if that makes sense. So going through some of the actual like APIs, there's a connection command, and I think this is up to date, but I can't remember. So if it's not, you can let me know. Here's the equivalent of the HTTP context in the low-level networking space. You have a connection ID. There's features. This is from the HTTP world. There's a transport, and this is an I-duplex pipe, and this is one of the new primitives that we kind of built into pipelines in 2.1. It basically has an input and output, so you can read and write from it and write to. And then each of these things are broken into features, just like the HTTP layer is. And the idea behind features is that middleware can add or remove features based on the underlying transport capabilities. So for example, a feature may be something like, I can provide you an IP address, because if you're TCP, I can give you an IP address. If you're not TCP, I can't give you one. So there are things that describe capabilities of the underlying transport layer.
So can I query?
Yeah, yes, you can. So you call features.get, and you pass in a T for a type, and that tells you like if you can get it or not. So I'll show you an example of some of the code we have in like a lot of screens. The code we have in.
Hey, by the way, do you have headphones available? You've got some with you, like our earbuds or whatever. If you can plug them in.
Would that help? The echo?
Yeah, that would get rid of the echo.
I'm gonna come back then.
That's my fault. We should have done that.
Yeah. There's nothing in here.
So to summarize on the chat for people watching the video, there's some MQTT. Frederick brought up MQTT is message queuing telemetry transport, which is interesting. There's a question about SignalR docs, and Damien jumped in and said that they're being written and will be published soon.
Awesome.
Yeah. That was quick. I thought I was going to need to fill more time.
I just ran outside, and then like James is here. James Newton King. He's
cool.
He just like threw me some headphones.
Oh man, we should get him out. How long is he?
He's here for 2 weeks. Yeah. We're gonna go karting and watch Avengers. I mean, do work, not that. Yeah.
We'll get him to call in.
Yeah. You can actually come by, say hi. I'll get him to come by afterwards.
Cool. Okay, so
where was I? I was talking about querying features.
Yep.
So as an example, we have some code. I'll just find some code quickly in SignalR core itself. We have some code I recall. I use VS Code now, like full time. I've not been using VS for a while. Wow. Because my computer is super slow, and whenever I turn on Windows, my computer starts like smoking, like it gets too hot.
Yeah.
So as an example, there's a feature called iTransfer format feature, and we say if you have it, then we use it, and this is kind of how you do that checking. So it's pretty simple. Get generic thingy.
So for if I'm writing a transport, I can. Or excuse me, not a transport. This would be the dispatcher that would be querying features.
This is the application itself.
Application. Okay, so in the application, I could query features available, and then I can say if I have support for whatever duplex or something, then do this thing. Otherwise, do this thing. Cool.
Yeah. So for example, we say, and this feature name is I didn't name this. This is Andrew. I'm gonna tell him that. Yeah. So this is an iConnection inherent keep alive feature. And the idea here is that if the underlying transport supports keep alives inherently, then we don't have to send heartbeats because it can be kept alive by itself. So we say if you have this feature and the has inherent keep alive flag is not true, then we don't have to worry about sending heartbeats. Otherwise, we get the heartbeat feature. If you have it, and we say on heartbeat, then we send a new frame, a keep life packet to keep the connection alive.
So, some of the goodness of SignalR is that it does all that graceful automatic fallback, right? And
Correct.
It uses different transports, and it says, okay, if we have sockets, do this. If we have this, do this, and it falls back. So what you're doing here, super high level, is you're abstracting that stuff out so that I can take advantage of that in other things, and also that that when transports are plugged in, it's not just kind of like the ones where you have hard coded into SignalR. It's more kind of pluggable into the transport itself.
Right. So, to jump forward a little bit. So in SignalR, so it's transports, right? So there is libuv and sockets. So today in Kestrel has two transports that ship out of the box in 2.1. Sockets, which actually use SystemNet sockets in CoreFX, and libuv, which is the thing we had since 1.0, and that hasn't changed. In 2.1, we're adding a bunch more transports, not to Kestrel itself, but to the Bedrock style ecosystem. So WebSockets, because SignalR itself exposes the connection abstraction over WebSockets. So we have to implement the same abstractions that we implemented in libuv in Kestrel for WebSockets and for the other transports, so server-sent events and long polling. And the interesting part is we actually give you like a socket-based API over long polling, which actually looks bizarre if you think about it, because long polling is a kind of a half duplex thing where you have one request outstanding for a poll and one request sending, well, not one request, n requests doing sends for incoming data. So we create the impression that you have a duplex transport over long polling and over server-sent events. So the APIs for the application look similar. So you code against this long-running connection that lives and gets bytes over and over and over in a loop. And then under the covers, that's actually sending multiple HTTP requests over the internet.
Wow.
Yeah.
So QUIC there, you called out QUIC briefly. There's a lot of excitement about that in the chat. And so people are asking, is it on the roadmap? And then Tarun's asking, if somebody wanted to help implement it, what could they do? What's the procedure?
Is it on the roadmap? It is on the roadmap. I'm not sure which roadmap. Maybe 3.0. We have so much stuff to do. HTTP2 is the next big thing for Kestrel. QUIC, I really want to have time to spike it. The protocol is changing rapidly. Like if you actually were to follow the W3C, like the whole process, it's changing a lot. At first QUIC used to have its own crypto, and then now it's TLS 1.3. So you have to kind of implement TLS 1.3 if you're going to do QUIC in the first place. And there seems to be only a few implementations out there. There's libQuic, which is a Go-based library. But if you want to build something, that would actually be amazing. So I would start by looking at the socket transport in Kestrel if you want to understand how to actually make this function, and then that'll kind of be a good starting point for making your own custom transport. I expect this will actually work well with our abstractions because it is connection based and you do have a connection ID. So I think that would actually work pretty well for this pattern, but we haven't actually done enough to verify that it'll work perfectly.
So if somebody really wanted to take a serious stab at this, would they, fork through the Kestrel repo or
no? So you don't have to. You could actually use the bits on NuGet.org in 2. I think we just did preview 2. RC1's coming. Yeah. So RC1's coming soon. Preview 2, you can start with that and then upgrade to RC1 when it comes out. And that pretty much has the final shape of the APIs you can use to code against. And then you have to implement this dispatcher layer yourself. Sorry, the layer that calls the application code once you have a connection object. So let me show kind of Kestrel how it looks. So Kestrel has this thing called Kestrel is this visible? Is good? Size. Kestrel transport abstractions, which actually this is all pubternal, public internal. it's there so you can try it, but it will change next release. I guarantee it will break. So don't be sad if it breaks on you. So here's the thing that lives in between Kestrel and the transports to kind of abstract Kestrel's core itself from the transports. There's this thing called transport connection. It has a bunch of goop. It derives from connection context, the thing that we saw before. It has a bunch of features. It does a bunch of weird stuff to optimize feature access. And it has a bunch of stuff on it, just properties that have to be set by the derived class. So in libuv, we have this libuv connection, which derives from libuv connection context, which itself derives from VS Code partial classes, which derives from the transport connection object that we just saw. And the goal here is to all of the transport you have to do is do your thing and then write and read bytes. And this you won't understand this code if you're not like into Kestrel or whatever, but as a transport owner, all you have to do is read from the application and write to your underlying transport and write to the application when you get data from the network. Okay. So this is kind of hard to see in libuv, but sockets may be a bit simpler now I think about it. So sockets has two loops: do receive, do send, and you can guess what they do. One thing gets memory from the input of some size, calls receive async on the buffer. If you're 0, you're done. Otherwise, you call advance and flush. And this is the entire read loop. Super simple, right? And then for sends, it's the same thing. We call process sends in the loop, and we read from the application, and then write to the underlying socket. And this is the code you write if you write transport. And how complicated it is all depends on how you talk to your underlying transport layer. But the end goal is to end up writing to the application and reading from it to do I/O basically. Okay. Yeah. So for this, while you're at it, and I may be in the wrong place, but can you show the code where it responds to the query features? Oh, I see. Yeah. Like, so if I query features, how is that implemented here where you say, here's what I support? So in Kestrel, it's a bit crazy because we are perf crazy right now. If I look at transport connection, I look at let me try this first. Features. So we actually, what we do here is we implement the actual feature collection interface and the features on the same object. So we don't allocate per feature. Okay. So you have one object that represents the entire the set of known features. And we have fields. So just in case that somebody wants to override one of those features. But by default, these point to the current object, if that makes sense. So if I look at transport connection without that layer, they all point to this. That's because by default, if no one overrode these features, it's the same object that's being exposed. Okay. So it's a way to not allocate a new object per feature. And then when someone calls get a feature, we have kind of this slow features that aren't known, and then we have the facet. So when you call get feature, it checks to see if the thing you passed in is this type. If it's a non-type, then we say return the value directly. So for the most part, for all known features, we just return this immediately. Okay. And then once you get to the point where we have unknown features, we say maybe extra not null, then we try doing a scan. This is cool. Yeah. I mean, this is pretty deep. Yeah. And the same for set. Okay. Set just sets the feature to the actual thing. And the idea is to avoid a dictionary lookup for the common cases. So my first thought would be that this is not something, this is going to be run not a whole lot of times, right? So right. Yeah, correct. But it is something where figuring out the feature set, if you're doing something in a loop or yeah.
All right, cool.
Yeah.
Sorry if I took you off the.
No, that's good. So let me show some working code maybe at this point before I go any further, so people don't get bored of staring at like stuff. See that? Is that size good? This is the wrong screen though. I want SignalR. All right, so I have some samples here in Sigma. Let me run these first. .NET run.
Maybe bump it up just a little bit more on font size.
Yeah.
Yeah. Sure.
.NET run -- framework, because we have more than one in our test projects. .NET Core App 2.1. That will start running. Let me show you the samples. Oh, where's my VS Code? Here. So let me find the SignalR samples. So I'm showing you the SignalR samples, and it has a program CS that looks like 1.0 because we write. Yeah, so our repositories in ASP.NET Core haven't been updated to actually use the new builder API. So we actually use the old manual ones. So here's use Kestrel on the builder, and I say listen localhost 5000, which is the web port. And in 2.1, we actually expose the connection builder abstraction on the Kestrel listen APIs. So I can say listen on any IP address, port 9001, and I want to get the builder, and I want to say use hub. And this is SignalR's framework code running on top of the connection abstractions. So SignalR has this thing, this use hub thing, and it has no idea what this builder is hanging off of. It could be TCP, it could be name pipe, it could be anything that can support the builder. Mm-hmm. And it just runs its connection handler on top of that builder. So it's kind of like the ASP.NET Core middleware pattern, where you have an I application builder, and then like there's use static files, and there's use SignalR, and there's various uses. It's the same pattern, but at a lower level, if that makes sense.
Okay.
And then if I show the startup class, I'll just show the startup class has configure services, which has add connections, which is the new low-level API. It has add SignalR. This is what we expect. And SignalR, I'm adding the message back protocol. It supports both JSON and message back by default. I have this commented out because I'm not running Redis right now, and it'll crash if I don't comment it out. And in configure, I have use SignalR with a bunch of routes. So for those who haven't seen the new SignalR, this is the new SignalR. You have to map specific hubs to specific URLs now. So I say map hub, the chat hub maps to default. If I talk on chat, it's a very simple chat application. When someone joins, I send connection ID join. When someone leaves, I say that person left. When send gets called, I send saying who sent it. And there's various groupings here. So send to others, send to everyone except for myself, send to a specific connection ID, send to a group, send to the others in the group. Then there's join group and leave group. So this is kind of showing off all the SignalR multicast functionality, where I can send to multiple people in a single call, or one person, or various sets of people, depending on what I choose.
Okay. One question there. You had all the routing kind of in code. Is there like an attribute syntax?
There is not, but I did find a bug to potentially, maybe, kind of thinking about could make this work.
Mm-hmm.
Yeah, but we punted it for 1.0.
Yeah,
and it seems too important. If it is, let me know, and I'll close your bug. I'm kidding. I won't do that. So now I should be running. So I'm running on two things. So I'm running on port 5000 localhost, and I'm running on 9001. Remember, we bound to this port in our in the program main. Mm-hmm. So I'm going to launch this URL. And this is our beautiful sample. There's no bootstrap because we're all lazy. And I'm going to use hubs. I'm going to connect. Let me open my tab so you can see the underlying connections happening. I'm going to connect automatic. In the latest SignalR in 2.1, we added back fallback to other transports. We didn't have it originally I think we didn't have it until RC1 actually, which you don't have yet. So in preview 2 or in the new SignalR 2, in the new Ethernet core SignalR, we were not going to do transport fallback, and then after a single release, we kind of realized why it was needed so badly. So we added it back. So there, you should be happy about that. This sample just shows various ways to communicate with others. So I can say, hey, I see it myself. You can see stuff going on down here in the actual tab. I'll get another tab because you can't have a demo with SignalR with one connection.
Right.
I'll connect here via long polling just because it's different. There you go. I join. I'll say hi. I'll broadcast that, and then this person sees that hi too. There should be keep life pings going on here. If I look at the WebSocket, here's the negotiate request that tells you available transports, WebSockets, source and event, long polling, and here's my connection ID to use for communication.
So in case it's not clear,
Yeah.
this one is communicating via WebSocket, but
Yes.
then the other one, when you showed it, excuse me, this one is long polling, but then the other one was, or
No, so this one is WebSockets, and this one is
the other
long
one
polling.
was long polling. Okay.
Yeah, so if I look at the tab here, I should have done it before. Let me refresh. I'll make this long polling. I'll connect, and you should see different things here. So notice there's a bunch more requests here, right? And there's responses. So guess not. Yeah, here we go. Here's the JSON response that came from the long polling request. Here's more requests that went up. And this I think this one is the pending request that's waiting for more data. So long polling works by having a request open to the server, waiting until data comes in. So this request is just going to hang there until someone sends data, or until I think 90 seconds goes, because it times out to avoid proxies killing it ungracefully. So and
then it just makes another request and hangs again, right?
Correct. Yeah. If I compare this to the WebSockets, where I can see frames, you can see the frames it's one connection, and you can see all the data going over it. And this type 6 is the keep alive frame that we sent. Remember the code we had before to see if your connection had inherent keep alive support?
Mm-hmm.
We do it for WebSockets, and we're sending this ping every. How long is that? I don't even know. I think it's 5 seconds, but it looks like faster.
Okay.
Yeah, so we send that ping every 6 seconds to keep the connection alive, so it doesn't die when proxies get involved.
Okay. And this is a much more lightweight ping than.
Yeah.
Okay.
Yeah, it's a very light ping.
There's a question in the chat. Is it a good idea to store the SignalR connections in its own list besides groups?
Yeah, if you want to have presence, like you want to know who's online, you have to store a list, because groups don't tell you who's in a group. It just lets you broadcast to that group. If you're going to do a loop and send to each connection in that group, that will not be as efficient as using groups. And it won't work cross servers so very well.
Okay.
So I would use a list of connections for if you want to know who's online or offline, but I wouldn't use it to actually do the individual sends, because that's not as efficient. If you can, like, you want to use groups to describe groups of connections in any arbitrary way that you group connections, and then send to that group, because we can optimize that instead of sending to each connection.
So looking at this and talking about stuff like groups reminds me of Jabber.
Jabber.
Did the experience of building Jabber like kind of inform some of the features and things that you're building here?
Yeah, so new SignalR, we were burnt. I don't want to say burnt. Old SignalR tried to work in all cases for everyone at all times in a distributed system, which made it really hard to scale to some kinds of applications. So new SignalR, our mantra was, let's start small. Let's start doing whatever you would have had to do manually. Let's see how bad that is. If it's really bad, then we'll add support for it. So as an example, we in the first preview, in the first alphas, we didn't support having the connection be reused. So if you made a new client and you call start, and you call stop, or if it went offline, you'd have to create a brand new client because we said, oh my gosh, reconnect was the hardest thing ever to do in the old SignalR. It had tons of bugs, it had tons of races, like all these things were wrong with it. And then after we wrote a single application, we realized, oh my gosh, this is impossible to use. Now we have to like do it ourselves again. And we kind of, but I think the big difference was as we did that feature by feature, we kind of decided that we were going to take on the burden of owning this space. Because in the old SignalR, we kind of just made it work and discovered bugs as we went, as time passed. Now we kind of understand the space more. We understand the types of issues that occur. So we kind of knew beforehand what we were getting into.
So yeah, it's a difficult balance because on the one hand, you're trying to build something magical.
Yes.
But then to do too much magic, you end up with complicated, hard to maintain code and it doesn't scale well and all those things. So this makes sense here. You've taken what you've learned from before, and then you're also kind of building simple and adding features or things as they're needed rather than guessing.
The biggest change we made was that new SignalR, if you do scale out, requires sticky sessions if you're not doing WebSockets. And that decision has simplified like everything else in the design. Old SignalR supported connections flip-flopping every single message between end servers. And it tried to support that at scale, which was like literally impossible. Now, if you do long polling or service and events, you have to make sure that you have turned on stickiness for those to actually work. And we don't have to worry about storing a client cursor that can survive reconnects across a farm. Like that I think was the thing that made SignalR as hard as it was to maintain now. So new SignalR just avoids that entire issue by not supporting it at all.
Okay.
Yeah. So this is cool. So I'll show. Let me try something else now. So I have two clients. I have the long polling client and the WebSocket client. Let me try doing one more client. So let me try opening a new window and going to. This is too small. Have SignalR samples, client sample, that run. And this sample is, I believe, going to use the TCP side of it. So remember we had two ports open.
Mm-hmm.
We had the port to 9001 and we had the port to 5000. Is that here? You see it right here? These two ports.
Right.
So this client, I have to say hub. This client should connect to the same hub, but be using TCP. So there we go. Net TCP, if you're a WCF fan, you will recall this scheme, this URI scheme. It's the same. This actually, so it's funny. I tried just TCP, like just doing TCP : like that pattern, and it blew up because you have to like register URIs in some API in .NET. If you do new URI, TCP : whack like address, it just blows up.
Huh.
But net TCP is actually hard coded somewhere.
Oh.
This works. So I was like, oh, cool.
So this is, instead of connecting at the HTTP level, this is going down to the TCP level.
Correct. So the same hub is supporting TCP clients and WebSockets clients and long polling clients. And the SignalR code has no idea what it's running on. It just is working. Right? I can say, hey. And there it is, right?
This is for the IRC level people that don't want to open up a browser or anything. They want to go straight to the console.
Yeah. I can send a message to this connection specific. I think this is my connection ID. I'm not sure now. Is this mine? Let me try it. This looks suspicious. There you go.
Wow.
All works. So SignalR itself is has no idea what's going on.
Okay, so it's all abstracted away.
Yeah.
As far as my job writing this chat client, I don't have to do anything special there.
Yep. That's right. And if you look at the actual code for the client, this is in a sample now, but we plan to actually do this in the next release. So the client side of SignalR, here's the hub sample. Let's look at the code here. So I create a new hub connection builder. I configure logging, add the console logger so you can see logs. If the scheme is NetTCP, I use with endpoint, which is a different API, and if it's not, I use with URL. So the client has a similar model to the server where I can plug in different transports depending on what I'm doing. And in this case, I'm using the URI scheme to determine if I should use TCP or HTTP or HTTP. So with the URL is built into SignalR today. It does the WebSocket fallback or service events or long polling, and this with endpoint is new. So I hacked together this sample. I basically copied Kestrel's socket transport layer and made it work for clients. So if your local host, use loopback. Otherwise, this actually doesn't work at all. But pretend it works. And then I add this TCP connection factory, which basically just starts a TCP connection, which is in the code actually in here, and called start async. And then this is all that SignalR needs to understand a new transport. And the idea is that we would have clients and servers be supported of various transports from the same interfaces. So today, the transport layers in Kestrel only support server things. We're looking at trying to figure out how it can support servers and clients. So if you want to create a libuv-based client, it would be the same APIs that we have today in Kestrel. You wouldn't have to go write that code from scratch.
Okay. Side question here.
Yep.
You had the command line options that had raw and hub.
Yeah.
Where did you implement that?
So in program CS, I think this is our command line helper that we have in ASP.NET Core.
Cool.
And it basically just has wait, where's the actual code that switches? Oh. Oh, it's here. Raw is there. Yeah, these two things.
Cool.
Yeah.
Okay, that's handy to be aware of.
Yeah. And there's one more layer of because layering is all I do. I basically create more work for the team. So every day I come to work and have a really bad idea, and then someone believes me, and then it becomes a thing. And then it's too late to not do it. So then we have to do it.
Hey, while you're bringing that up, there's a question on MQTT. So you did talk about it. What's the to summarize? What's the level? Is that kind of something you're thinking about? Is that on the roadmap?
Good question. So it's not on the roadmap, but
it's on the backlog.
But the backlog, by the way, is very buzzword to die. So if you were unaware of the state, so this guy Jan, I think it's Jan Eggers, actually this is really cool recently. He took SignalR's protocol parsing layer and gutted the protocol itself to support MQTT. And then he still used hubs as the dispatch model. So he wanted to use a hub with methods to actually call into as the API that was exposed to end users. But under the covers, it was handling MQTT as the protocol.
Wow.
So here is this playground.core. And it has this MQTT. Let me find it. So first of all, here's the MQTT parser, right? This actually takes in the bytes and it parses the packets and it understands the protocol. So this is kind of one area. And then there's how does that plug in? How does that plug into the actual pipeline? There's this thing called an MQTT.
There's a lot of work here.
Yeah, yeah.
So could this be pull requested into? I mean, possibly.
We have to figure out how it lives first, what it means, because this is kind of a hybrid of using hubs solely as a model to dispatch to your methods, right? But it's actually using SignalR. It's using the SignalR programming model, but it isn't using SignalR itself. So he replaced the actual SignalR protocol there with this thing that understands MQTT. So as an example, and this is an example of having to write the code that understands the bytes on the wire to parse, right? So you get an MQTT hub connection context. You read data from it, you get a buffer. If it's not empty, you deserialize packets off the buffer. So a packet is basically his MQTT packet. And then he has a method to dispatch to that thing. And then it says, if it's a connect packet, call on connect. If it's publish, call on publish. If it's ping, call ping. If it's subscribe, call on subscribe. Otherwise, like nothing, right?
Okay.
And then from here, the question is, once you get a packet, what do you want to do with it? Do you respond to the client, or do you call into some framework, right? And what he wants to do is he wants to use hubs as the model. So I believe there's some code that says, do some stuff to preprocess and then call into the hub pipeline. So then there's this thing called an MQTT hub that he instantiates. And it basically has a bunch of methods to handle MQTT specific like payloads, right?
Oh.
So I could see this is either a SignalR like extension, or it's a different framework, right? That looks similar but is different, right? What is the controller base class for arbitrary server protocols? That's kind of the question, right?
Yeah.
Because this is a hub. The whole idea behind the hub is that it was like a controller. It was this place you can write code as you get invoked, right? It's the same thing here, but you aren't using the hub semantics per se. You're just handling this protocol, dispatching the methods.
Okay.
Yeah. So it's not on the roadmap. I think there will be interesting things that happen in the community. I think we'll watch that and then decide if we're going to take it in or not based on demand.
Okay.
But I really want SignalR to be a super fast, low level, light layer on top of the transport that is extremely reliable. So you can use it to handle connection disconnects and send payloads back and forth. And you don't have to worry about having your own protocol because we support dispatching methods for you.
Okay.
On top of that, it is kind of up to you.
So we're coming up on an hour. We have,
Yep.
we can go a little bit longer or whatever, but did we cover all the stuff that you want to cover? Is there more stuff you want to get to? Because I've had asked some distracting questions along the way.
No, that was good. I had a bunch of random things in case we didn't have enough time, like pipelines, in case people want to know like what it was. I kind of want to show one thing.
Sure. Yeah. I mean, we've got a little time. We've got 5 or 10 minutes, but I just wanted to make sure we cover everything you want.
This whole thing is blank out. Is it working? Can you see this?
Yeah, I see the system IO pipelines.
Yeah. So this presentation was given by one of our developers, Pavel. He gave it to the .NET team at one of our internal talks. And I don't plan to go all the way through it, but I think we have been talking about pipelines like just on Twitter every now and then for a while. And some people want to know like what the state of it is. Pipelines is shipping in 2.1 as an like official supported CoreFX library. It's right now on NuGet.org in preview status. So it is preview 2 currently. It's used in Kestrel, it's used in SignalR. It's actually used in a bunch of places in ASP.NET Core now. So you can feel good that it's been like battle hardened, hopefully. So I'll kind of run through like what it is quickly because I don't want to spend too much time going through like specific details. So as part of that whole move to CoreFX, we basically made a bunch of primitives, not just pipelines, but things like buffer pools. We made a bunch of abstractions for doing efficient networking I/O. So let's go through this quickly. So today, the issue with streams are that when you call read async, you have to actually pass in a buffer to stream. Some streams have a buffer internally, which means you end up copying from the buffer internally to the one that you passed in. And that can happen at multiple layers, and you have no idea when it's happening. So when you wrap streams in other streams, you have to kind of understand how the stream is written to understand if you are buffering too much or not. The buffering can be good or it could be bad. But for some scenarios, for example, WebSockets, we kind of don't want to allocate anything unless data is coming in. So we kind of want to avoid that whole thing. Um,
By the way, Tim says
Yeah.
he can confirm pipelines work in production.
Yeah. Okay. Yeah. Tim is crazy because Tim put it in production probably before like it was even baked. So yeah, I agree. Good. Awesome. No common pattern for pooling. So if you want to do efficient networking I/O, you normally have to pool buffers, and you have to either create a memory pool or use one that's out there. You have to rent and return. And once you start pooling memory, you're in the realm of C++, malloc free. You have to understand when to return memory. Mm-hmm. And it's very simple if you are your own component. The moment that data is passed somewhere else and it's pooled, the consumer has to know when to return it. And when do you return it? Like today, the GC understands it knows who's using a thing because it can track usages.
Right.
That's all gone here, right? You've kind
Once I'm managing my memory, I'm managing the memory.
Exactly, and that is actually a really bad place to be in. So part of the goal was if you want to do efficient networking, you have to pool buffers. So how can we make the model such that if you do pool buffers, it's kind of hidden from you, or that it's natural, right? The rent and return semantics are natural instead of being a very explicit operation. Today, well, in 2.1 it's a lot better, but in the existing world, you have to allocate a task per read or per write, and that was kind of a thing that we didn't want to do. So in 2.1, value task actually supports this very optimized code path where the value task can represent multiple async operations without having to allocate it. So that's actually the abstraction we use now in pipelines. But before that, there was no way besides writing a custom awaiter to avoid allocating a new task every time you did a read or a write. And that adds up like quickly. Cancellation tokens have been kind of fixed in 2.1. They aren't the best API though, because APIs that implement cancellation have to account for passing in a different token every time. And that kind of makes it less optimal. And then the other thing was that every time you want to implement cancellation, you end up throwing exceptions, which kind of sucks if you want to cancel a thing that isn't exceptional. So you end up throwing exceptions for known cases, which kind of sucks. So in pipelines, we never copy. We actually give you the buffers. So the switch here is that before you'd have to pass in a buffer. Now buffers are fed to you. So you don't end up having to allocate buffers because that's done under the covers by the actual APIs. It does mean you have to trust it. Most of the APIs you can configure. So you kind of configure it once, saying, I want you to allocate memory like this, with this pool, and with this size. And then all consumers from there on out get buffers passed to them instead of having to allocate per call. You can read data without consuming. This is super important if you're parsing protocols that are stream-based. What I mean is, suppose you're trying to parse a protocol suppose you're trying to parse a line-based protocol. So you're looking for a /r/n at the end of every packet, right? Mm-hmm. Imagine the client sent 2 bytes that didn't have a /r/n. So you read 2 bytes off the wire, and then you have to keep buffering that until you find a /r/n, right? Doing that efficiently, where the client can kind of send you tons of data, where you haven't seen the actual new line for a while, you want to actually allocate that buffer in chunks so you don't have a giant buffer allocated on the heap in memory, right? So the pipe lets you actually read ahead and say, okay, I read these 2 bytes, I didn't see a new line, I'm going to wait. So you can kind of put data back and have it be buffered for you until you see what you care about. There's no allocations per read, per write. The per operation allocations are gone. We internally store the buffer as a linked list of chunks to avoid allocating giant buffers in memory all at once. Cheap cancellation, there's no exceptions, no allocations. It just yields the current read. So if you say cancel, it'll return you a result saying, oh, I canceled, instead of throwing an exception. So it's cheaper. Okay. This is supposed to be a comparison showing you, it's kind of a bad comparison, but the imagine you want to read stuff from a file, a 10 meg file. The bottom is supposed to be stream reader. So you open the file and then you call read line async, super simple API. The pipe API is a bit more verbose, but the idea is that you would re-implement stream reader on top of the pipe API, if that makes sense.
Okay.
So
and in that case, I'm not allocating.
Right. So as a comparison, and this is kind of the code continued, right? There's a bunch of other code to read lines and stuff. So ignore the bug. That bug is fixed now. So erase that line completely. the top row. It's the same file size in both cases. So the strings are all the same because we do turn the line into a string eventually. And the only thing you pay for in the top is really like the file reading. But the intermediate allocations are all gone.
Okay.
So there's no string builder, there's no task from async trim promise, there's no read write task, there's no the allocations are cut down like significantly. So
to kind of talk about this at a simple level, this is kind of like span of T, but for things like kind of communication.
For streams, for streams, yep. Yeah, actually, cool. That's a pretty cool comparison.
Okay.
And then we have some history here, kind of the same thing from my previous document. Socket input into Kestrel, channels, CoreFX Lab, pipelines, public API in 2.1 in Kestrel and SignalR. Copy list, and this diagram kind of shows what we mean by copy list. Today, you get data from a socket, and it has the HTTP start line, and it has some stuff in the body, and it has a chunked header, right? Some chunk stuff there. In a world where you have streams, you call read async, you pass in a buffer, it will copy from that internal buffer into your buffer and hand you some data, right? What if instead you could just parse the bytes in place? So I read bytes from a socket. I'm going to read that same buffer and parse HTTP up until the new line at the end of chunked, right?
Right. Okay. Yeah. So I'm directly accessing that as opposed to getting a copy of that string passed to me.
Correct. And then the next layer gets access to the body. So in ASP.NET Core, the way we handle the HTTP pipeline is Kestrel reads the start line and headers, and then calls your callback, right, to run middleware. And then when you call read on the body, then we give you more data, right? But it's the same overall request, but they're kind of exposed from different layers. So you read the body, and now you get the same buffer, but you're reading that chunk that says 15, DA, that data, hello world. And now you pass it to a JSON parser. It reads the same buffer, but now only the part that has JSON, not the entire chunk, right?
Right. This is a really cool, this explains it really smoothly. This makes a lot of sense.
Good job, Pavel. Good job. This is the whole peaking aspect. So I call read async. I get GE because the client didn't send get yet. They just sent GE, right? So I tried parsing that to the parser, and it says that's not a full HTTP request. Go away, right? And now I say, okay, I'm gonna advance to the start of the buffer, which says I'm gonna put back all this data because I consume nothing. And now I call read again, and now I have more stuff. I have get/rn, right? Which actually isn't a valid HTTP line, but I'm gonna leave it for now because it doesn't matter for this example. I call try parse again. It says, oh cool, I have a full start line. Now I call advance to end because I consume that entire buffer.
You're marking that as red at this point.
Correct. And the cool thing about this pattern is that when you call advance to end, it actually will return blocks to the pool under the covers. So that's your rent return semantics, right? When you call rent or from a pool or allocate is when you're on the other side writing data into the pipe. When you call advance, it actually just returns as you've consumed. So you're kind of shooting from the actual allocation and deallocation APIs completely.
Okay. And because of that whole kind of rent semantics, if there were multiple people accessing this stream, I would say I'm done with it, but it doesn't necessarily return it It doesn't mess with anyone else that's accessing.
You would, okay, so you can't do it in parallel. This API only supports single reader, single writer at a time.
Okay.
So it's more like you would do that sequentially. So I would read one part of it and then pass you the rest of it.
Okay.
Right? I'll read again. I get the body. The headers. Yeah, and then I could pass that API onto the header parser, and it would understand just the headers without having to reallocate more data, right? You keep reading the same buffer over and over. Push and pull. This isn't that important. I'll skip that for now. There is this idea of back pressure where, like, as you're pumping data into the person that's reading, we have to support a scenario where you can overwhelm the person that's trying to read data. So imagine the socket is sending tons of data over and over and over, and the consumer can't keep up. There has to be a threshold, right, where you stop. Where you say, okay, bro, I can't handle any more data. Let me stop and back off, right? So that's the pause writer threshold. So when you hit that threshold, the person producing data stops until you reach the resume threshold. So the idea is that the consumer is reading data off of the network, and I'm trying to parse HTTP, but my app is running very slowly, and I can't do it fast enough. So please stop. Handing me more data while I'm trying to process this stuff. So you set a maximum threshold, so that the transport layer can stop pushing data into the pipe over and over and over. Make sense?
Yeah. Yep.
Yeah. We have this so there's span and there's memory, and there's a type called read-only sequence that represents a buffer chain. It's basically a single view over a linked list of buffers. And this is the type that pipe exposes to end users when you call read. So it's basically a view over this chain of memory.
Okay, so it's abstracting that out, so you can do the things previously, like you were showing, where you can read just a chunk at a time or whatever.
Yeah, so you can copy or slice, or the APIs kind of look like span and memory, but they're on a chunkier type.
Okay.
And there are these things called positions that kind of tell you the beginning and end of the actual sequence. So, for example, the pipe has a bigger view of memory than the actual sequence. The sequence only is exposing a subset of the overall data in the pipe. So here's an example of our read-write loop. Ignore the API calls because the API calls have changed slightly, but it's not super important to the actual scenario. So here I have 3 pointers: start, end, and writer end, right? So the writer is going to get memory from the pool, and it's going to write 1, 2, 3, 4, 5 into the actual pipe, right? Make sense so far?
Mm-hmm.
So the start and end haven't moved, and the writer is at the fifth block in the memory pool. Now the writer writes more data, 6, 7, 8, and that ends up going over the block size, so it ends up being part of this linked list now. I call flush. Flush says I want to make this data visible to the consumer. So by default, as you're writing, the consumer can't see it. It's only when you call flush that the consumer can actually see data.
Okay.
So now the reader is reading, and it can see 1, 2, 3, 4, 5, 6, 7, 8, right, in this chain. It reads up to 5. And it says, I don't have a full frame for 6, 7, 8 yet, so I'm just going to not read it. So I'll advance to 5, right? So now the start pointer has moved to 6 because that is the end of where the reader saw last time, right?
Right.
And now the writer is going to write some more and then call flush. So now the reader can see 6, 7, 8, 3, 2, 1. And now it has a full frame and it can parse it.
Okay.
And it's happy. So that's kind of that's basically the flow when you're using pipes to process I/O.
So this is something where, like, definitely down at kind of the transport layer and stuff like that, that's useful. Are there other places for a pipeline where, like, you know, your average app dev is going to, like,
Yeah.
You're going to want to use this, or is this more kind of like a library transport level kind of?
No, so the thing you said about being the span of streams, is interesting. We actually want to expose the pipelines from the HTTP context request body for the bodies of the request and response. So the idea there is that today we have a stream that we expose as the body. So if you did like HTTP context.request.body, right, that ends up being a stream. So let me just, whoa, 3, 2, awesome. If I show, let me find a sample. If I look at, close this. If I look at HTTP context dot, where is it? Up here. If I do context dot request dot body, this type, this is a stream, right? So what ends up happening is that since ASP.NET Core is so layered, we have Kestrel, then we have middleware, then we have like MVC, right? So we end up having to, in our own code base, in our own layers, we end up having to copy because we kind of have hidden the abstractions away from the user code. So the idea would be we actually expose the body or a new property, right? A new feature as a pipe reader or a pipe writer, basically for input and for output. And with that, our middleware itself can take advantage of it. So for example, MVC can now read the bytes directly from Kestrel and model bind that into the objects. So it is kind of exposed to end users, but they don't have to use it themselves because we're gonna, since they live at such a high level, where if you do model binding and MVC, right, you don't have to do with streams ever. You're doing objects. But you get the benefits because if we can get access to those low-level APIs inside of middleware at that level, then we can write super efficient parsers for JSON, for form, for various things, without having to reallocate memory that's there already for us. Make sense?
Okay. Yeah, that makes sense.
Yeah. But the average dev won't have to use it for most things because it's basically if you interact with streams today, then I can see a world where you consume pipelines instead. But beyond using streams directly, if you're just using like JSON in, JSON out, using model binding, you wouldn't directly have to use these this API.
Okay, cool. Well, so we're at 1 hour and 15 minutes. We should probably kind of wrap up here. Plenty of stuff. See, and you were worried about having enough stuff to talk about, right?
Yeah.
This is great. Well, a lot of feedback on the chat. People love this. So we'll definitely have to have you back on.
Awesome.
So let me see. Can you share with me your some of your links, and I'll make sure to put those in the chat here or in the
can do
thing. Cool.
Awesome.
All right. So we need to switch off your screen sharing, and we can do dramatic zoom out.
Zoom out this thing. Where is my like Hangout? Oh, I found it. There we go.
That's me. That's not you. That's me.
Wait. Got it.
There it is. All right.
Ooh.
Yeah. Okay. Awesome stuff. Okay. So you need to zoom in on you.
Zoom in first?
Zoom in first a little bit so that it's more dramatic when you zoom out. Okay.
Oh.
All right. So here we go. Ready for the dramatic zoom out?
Ready.
Dramatic zoom out. It's so dramatic. That's kind of slow, but
it's so slowly.
It's a rather undramatic. There it is. Dramatic.